Hello and welcome to our webcast series 35 brought to you by ROHDE and SCHWARZ. My name is Andreas Rösler. I'm a technology manager and I will discuss with you a topic today that is a buzzword in the wireless industry. It's called dynamic spectrum sharing, and we'll look at the fact how NR, 5G NR, new radio and LTE can coexist in the same spectrum applying this technology feature. So what you see basically here is the spectrum holding of the US service providers, Verizon Wireless, AT&T, Sprint, T-Mobile, and so on. It's just an example. You can paint, of course, the same picture around the globe. And you see the availability of spectrum to them. And the majority of the spectrum is frequency division duplex organized. That means I have a paired frequency band, a downlink and uplink are separated in frequency. And that is the case for about 90% of the spectrum below 6 gigahertz. The only exception is the TDD spectrum, the unpaired spectrum that was kind of underutilized in 4G LTE and was used for the initial deployments of 5G new radio using non-standalone mode, sub 6 gigahertz frequencies in or around the world. But in the US, it was only deployed in millimeter wave using LTE. Here, these frequencies are using 4G LTE, as I mentioned, as an anchor band. So the challenge for US service providers and others around the world is now to utilize the existing low band spectrum, low in this case I mean sub 6 gigahertz, to deploy a 5G new radio coverage layer. So what kind of options you have as an operator is basically two. You either acquire new spectrum, that is sometimes challenging, we just can't make more of it. And in the US, for instance, there's only one auction coming up later this year about CBRS, about 3.5 gigahertz. That is only a certain amount of spectrum available. And the other option is to switch off any of these LTE carriers that you deployed in these different bands and refarm the spectrum. You have to clear it first and then refarm. And that has, of course, an impact, negative impact on system capacity because you take spectrum away and you still have the majority of your subscribers on LTE. And so you need that capacity. So the question is how to overcome this, and the solution, the answer to that problem is using dynamic spectrum sharing. So dynamic spectrum sharing, what is it? Today, I already described that. The spectrum LTE is deployed in all of these bands. These deployments are combined through a feature called carrier aggregation that has been added to the LTE specification with 3GPP release 10. You see an example, very simplistic. Two bands, band X and Y. Replace X and Y with your favorite band numbers. And then you have your band combination. And as you can see, they can be of different bandwidths and be aggregated to create these wider data pipes. There's enormous number of these band combinations based on the operator preferences. There's, of course, the possibility to aggregate more than just these two shown here. Like I said, I do a simple example, and that has been the challenge for the industry to test all these different band combinations and such and make that work within the different smartphones and networks for the recent years. So now you can say, okay, if I want to share the spectrum, I can do that either in an FDM, so in a frequency duplex mode, or in a time duplex mode. What does that mean? So for instance, FDM, if I have a 20 megahertz carrier, I simply say like, okay, I allocate 10 megahertz to NR and 10 megahertz to LTE. Of course, that would have an impact to hardware and such, and of course would also mean that you introduce a capacity limitation to both technologies. Your peak is still on LTE, your majority of subscribers are still on LTE, so now you're taking half a carrier away. That would impact capacity in that cell, and you have only a few subscribers on 5G at the beginning. Of course, that's ramping up while you're transitioning over, but at the beginning you basically do not a very efficient way of using the spectrum. Same applies, of course, if you do just a TDM approach. We have technology features in LTE like MBSFN subframes that are intended for broadcast, a release 9 feature, which means that there's no standard LTE signals being transmitted in those particular subframes, so they could be then filled with 5GNR, kind of misused if you like, even if that is a very negative word. But in this case, you're doing the same thing from a perspective. You allocate resources from a time perspective, and you would also only have a few resources available for 5GNR in the beginning. But the question is what you're doing at a later stage, as the MBSFN subframes that could be configured to become MBSFN subframes are limited by the specification. So long story short, the idea is to combine both approaches within dynamic spectrum sharing. And the dynamic aspect comes now with the use of smart scheduling algorithms that are intended to balancing the resources among both technologies that are available based on several parameters, like load situation in the cell, for instance. But later on, a few more words about that. Dynamic spectrum sharing is enabled by a number of features that are listed here on this slide. Some of them apply to LTE, the majority of them to NR. So on the LTE side, we need to activate these broadcast subframes that I briefly mentioned already. And then to understand the feature, we need to take a look at the different mapping types for the data channel in 5GNR. Also mentioned the core sets, that means the control channel, and how is that being utilized. Talk about some rate matching and some additional positioning for demodulation reference signals. And then in the uplink, we need to align the channel raster to support the uplink scheme in LTE. As you may know, in 5GNR, the uplink access scheme is OFDMA, same as in downlink, but in LTE it was single carrier FDMA, and that applied a 7.5 kHz shift to the subcarriers, which needs to be applied to enable the sharing also in uplink direction. So let's take a look at the individual features and start with the broadcast subframes on the LTE side. So if you look at these MBSFN subframe configuration, as it is called, so first of all, that's being broadcasted into the LTE network with the help of system information block type 2. The graph here on the side is an example to illustrate that configuration and the flexibility into configuration. So we see here I plot a radio frame of 10 milliseconds, and then I also plot a number of system frame numbers, so it's time over time if you like. And as you can see, a radio frame in LTE is 10 milliseconds long and formed by 10 subframes, so that means a subframe is 1 millisecond, of course. You see here some of them are gray, in particular subframe 0, 4, 5, and 9, and that means they are not available as broadcast subframes, so they can't be configured for that. The reason is simple. In subframes 0 and 5, for instance, we have the synchronization signals, the primary synchronization signal and the secondary synchronization signal transmitted for LTE, as well as in the first subframe also the broadcast channel. And then in these other two subframes 4 and 9, they are typically utilized to page a mobile into the radio cell, so they need to be available for LTE. So that simply means we are left with 6 subframes that can be configured for broadcast purposes. On the LTE side, I said that was the original intent of it, so you see them here, 1, 2, 3, and 6, 7, 8. And their configuration, so which one of those, the periodicity, over how many radio frames this is allocated, if there are any offsets, that is all being given towards the device based on that MBSFN subframe configuration information element that's available in zip type 2. And at the end of the day, it's being coded into these particular bitmaps dependent on the allocation mode, which could be either 1 radio frame or 4 radio frame, like here in my example. So in that case, you would have then 6 times 4, so 24 bits available to create a scenario like that. So that is what a LTE mobile has to read in order to understand which subframes are still standard LTE subframes and which are broadcast subframes. And it can simply ignore, for instance, for channel estimation purposes. So now the question is why we need actually these MBSFN subframes. Answer is simple. We need to allow a 5GNR device to establish synchronization, initial synchronization, and carry on with the initial access procedure. So fundamentally, in the initial DSS deployment phase that is anticipated for the second half of 2020, we need to understand that the numerology between the LTE carrier and the 5GNR carrier is aligned. In other words, also 5GNR will use a subcarrier spacing of 50 kilohertz, and in that case then also the same bandwidth notation than the LTE carrier that it should share that with. From a technological, from a standards perspective, there could be a mixed numerology. That means, for instance, the 5GNR side could use subcarrier spacing of 30 kilohertz, where on the LTE side we of course are bounded to the 15 kilohertz. That's possible, that's standardized in the standard, but initial deployments will only use an aligned numerology. So back to the MBSFN subframes, why we need that? We need to be able to transmit the synchronization signal blocks in the downlink. And they have a certain mapping principle based on the subcarrier spacing, based on the deployment frequency range that you can see here. So for 15 kilohertz, it's called the case A. And for deployment frequency range below 3 gigahertz, they're at maximum 4 of these synchronization signal blocks that can be transmitted, and they are transmitted in a time division duplex, so after another with specific mapping principles. And these mapping principles mean that the first 2 SSB indexes from the total available 4 would fall actually into the first LTE subframe still, which can't be used for broadcast. So in other words, we can't transmit these first 2 indices, these first 2 SSBs at all. So that's why we are bounded to the fact that we now need to configure the MBSFN subframe to be the second subframe, as you can see here. And in that subframes, we would then be able to transmit synchronization signal blocks. However, that is also not that trivial, as we need to keep in mind that even an MBSFN subframe has a so-called non-MBSFN region. I marked that here in dark blue. And that dark blue means there's still an LTE control channel being transmitted, as well as LTE cell-specific reference signals. So the first 2 symbols, as you can see here, up to the first 2 symbols, could be still required for LTE, and that is of course something that we need to keep in mind while we then map to the remaining 14 symbols in that subframe, in that slot, our 5G and our technology as shown here. What else are the MBSFN subframes required for? Well, besides the synchronization signal blocks, there is also the need for tracking reference signals. In 5GNR, there are no cell-specific reference signals anymore. It's a thing of the past compared to LTE. In LTE, they're omnipresent in time and frequency domain. And so in NR, we configured actually channel state information reference signals, so-called CSI, to be used as tracking reference signals. So they are not that frequently transmitted. From a time perspective, the default periodicity is 40 milliseconds, and if they are used, the CSIRS, are used for tracking, then there's a certain definition how to apply them. And here's a nice tool that ROHDE and SCHWARZ application engineers are using to map out the configuration of certain signal components, and I'm using that here to illustrate the settings for CSIRS as tracking signals. So first of all, they can be occupying certain symbols within that slot. For instance, the pair of signals that is needed can be symbols 6 and 7, and I'm actually configuring that here in my screen, where I'm saying I want to have that first symbol 6 being used for CSIRS according to that configuration. So then you see for tracking, they would use only a single antenna port, a density of 3, no CDMN type 0. So I'm basically configuring that down here in these two different paragraphs as shown with the density of 3 and no CDM. And then there's this 4-bit long bitmap that actually tells me which of these subcarriers in a resource blocks. So this is a resource block, this is a slot. Which subcarriers in the resource block are doing this, and this bitmap is actually on the top of this particular tool. And based on that configuration, that 4 bits, in my example 0001, it is that the first subcarrier in a resource block carries that, then the 4th subcarrier, and then the 8th subcarrier carries a portion of the CSIRS sequence that's being used for these tracking reference signals. And like I mentioned, the periodicity is up by default 40 slots, in other words 40 milliseconds in this case. So if we take this as granted, then we see now why we need actually 2 MBSFN subframes here, because on the definition of tracking reference signals, I think I haven't mentioned that, I need 2 resources. So you see that here, symbol 6 and 10, 2 resources in 2 consecutive subframes or slots being transmitted for tracking purposes. That was the definition that you could have read on the previous slide, and that's the reason why I now have 2 MBSFN subframes configured here. Overall, of course, this has an impact on how many MBSFN subframes I need and how my MBFSN configuration looks like. So if I summarize that and look at this, so I have an allocation period here over 4 radio frames. My SSB periodicity is 20 milliseconds, so I need every 20 milliseconds an MBSFN subframe to transmit my SSBs, and then I need TRS to do fine tracking of frequency and time, and that default periodicity is 40 milliseconds. So that's why you see here every 40 millisecond would be an MBSFN subframe required, and not just 1 but 2, because I need to have 2 consecutive slots available here to do the TRS. So this is the simple configuration for MBSFN in terms of DSS needed. Here you see what would be transmitted in an SIP type 2. As you can see now, if you want to talk a definite impact of DSS, enabling DSS in the LT network side, we basically can now see that we have in the configuration that I'm using here as an example, we have a total of 40 subframes available, where we're using, out of the 40 total one, 3 subframes for broadcast, so, or configure them at MBSFN. So if I do the simple math, this is 7.5% of my capacity. So a single digit number that we take away from LTE, and that will be fully occupied by 5GNR on a periodic basis. So of course, if we just take that, then of course our capacity on the 5G side is limited. Is there anything that we can do about that? Or in other words, the question is, can 5GNR use a standard LTE subframe? So that means anything else that is not framed in blue here or has a blue background color. And the answer is yes. The challenge, of course, is the LTE physical layer design. Then even if the scheduler doesn't schedule any PDSCH in there, we still have control channels being left. We have still the LTE cell-specific reference signals omni present. And we also have certain mapping guidance on principles how to map the data channel in 5GNR and the related or required demodulation reference signals for the data channel in 5GNR. So if we take a close and quick look here on that configuration, how it could be configured in 5GNR, you see a lot of flexibility, not just by looking at this eye chart, heavily crowded with information coming from the different specifications. So we're dealing initially with two different mapping types, mapping type A and mapping type B. Difference is only mapping type A is where that mapping starts with the slot start. Mapping type B is relatively speaking where the PDSCH starts. So in my example here, the PDSCH starts at symbol 1. So that would be, if we define mapping type B, my reference point for mapping type A, then of course the slot start, which is symbol 0 right here. So long story short, as you see all the shaded, greenly shaded resource elements here with different patterns could become a resource element that carries a portion of the DMRS sequence, so a very flexible mapping is available. The question is, and why I'm talking about this, is this mapping flexible enough for avoiding LTE cell-specific reference signals while we're trying to put 5GNR into an LTE standard subframe where this is present. So let's take a closer look here on the different definitions. So again, an NR slot uses always 14 OFDM symbols. And in case of the same numerology, in 5GNR and LTE, like I said, they sharing in the beginning the same numerology, 15 kilohertz. A slot in NR corresponds to an LTE subframe. So typically in LTE, if we assume that the first symbol is still occupied by the control channel for the ACK-NAX being sent for the uplink data transmission on the hybrid ARQ indicator channel, for instance, there's always a symbol needed for that. So if you assume that the first symbol within the slot is always occupied by the PDCCH of LTE, it leaves 13 symbols left for 5GNR for the data channel. So you see that basically here in the example. Now, since we have a mobile system, one reference signal for demodulation purposes, so for DMRS, is not suitable. So we need an additional position marked here by the additional position 1. And if we look now into these area here, there's L0 and L1 being mentioned, and the question is which symbols are these for deployment. So L0 is coming with the master information block, could be either symbol 2 or 3, and L1, as shown here from the specification for mapping type A, is symbol number 11. So let's take that information by standard 5GNR terms and put that onto our map here. So now we are looking at an LTE standard frame where we want to put 5GNR in. And if we look 5GNR, we still have our first symbol, like I initially mentioned, occupied by the LTE control channel, and in that case there are also the cell-specific reference signals being present. But the remainder of that slot or subframe can now be used for NR. And like I mentioned, the initial position L0 is given by the master information block, in which we decode from the synchronization signal blocks in 5GNR. So you see here that could be position 3, which means symbol 3, as you can tell. And then we would have a symbol number 11, like I said from the table that we saw on the previous slide. So as you can see, this particular symbol 11 has still the LTE CRSs being present, right? So you see them right here. So if we would not now map our DMRS signal into that particular symbol, we would have a challenge, and we would create interference, and we would have a problem at our hands. So the solution to that, as you already can tell from the graph, is basically moving the position from symbol number 11 to another symbol, and in case of DSS, in case of the 5GNR standard, that is symbol number 12. So that has been agreed by the standardization group, by 3GPP, when two other conditions are met. So first of all, like I already said, the initial position for the PDSCH-DMRs needs to be symbol 3, which is coming with the MIP. So that's why we have seen it on the previous slide. In today's normal networks, it's symbol 2. So it's an indicator. If you look at this network configuration, if DSS is enabled or not, it's not the yes or no answer, but it's an indicator. And the second prerequisite is actually mentioned here, that the network needs to configure rate matching for LTE cell-specific reference signals. Words to that in the next slides. So what that means is that a UE that is capable of DSS definitely to indicate this functionality support towards the network. So that's something that you can check for while you're doing capability testing, checking on the device during a lab-based testing of a 5GNR device. So a device needs to indicate that to the network, and these two preconditions have been met to be met in addition. So the question is like, what is that LTE CRS matching and what it is good for? So what it is good for, it's actually the solution for mapping the data and avoiding the LTE CRSs. So in generally speaking, these rate matching is configured via the RC connection. UE could be configured with up to 4 rate match pattern, and for DSS in particular with an LTE CRS rate match pattern. So basically avoiding all these resource elements that are marked here with purple, that mark the position of the cell-specific reference signals in case of a certain MIMO mode is enabled. So the configuration, as you can see here, is coming with the information on what frequency bands are is used for the standard. What's the bandwidth? The MBSS subframe configuration is important because in those no LTE cell-specific reference signals are present. Then the MIMO mode, in this case 4 antenna ports, so LTE MIMO mode 4x4 is used. And then last but not least, this starting point for the LTE CRSs is dependent on the physical cell identity. It's called the V-shift, and therefore that information needs to be given to the device as well. So what we see by that is this is all what is necessary on the air interface to apply this particular configuration. Beside the air interface, we have core network aspects. Very much in the case that there could be 2 different vendors be used, one for LTE, the other one for 5GNR, in which case they need to perform a resource coordination procedure over the X2 interface to secure or check which resources can be used or need to be used by LTE and which can be used by 5GNR. Again, this is only required in a 2-vendor case. Typically, if it is one single vendor that provided 4G LTE and that provides 5GNR, then they have own internal proprietary methods to enable these sharing possibilities. But stick to the specification. What is important here is that we have a sharing bitmap in case of 5G and DSS. It would be applicable to uplink and downlink, of course. And the most important one is these bitmaps that you can see here for uplink and downlink, which result into this particular specification definition, which could be up to 17,600 bits. And like I said, it's hard to read that in a 35-minute webcast. So what it says here is basically each bit stands for a pair of resource blocks across multiple subframes, and therefore indicates if it is set or not, if this resource is used or intended to be used for EUTRA, for LTE, or in other words, it is available for 5G NR. So here's an example of such for the different bandwidths that LTE supports, how these bits can be used and what the numbers of addressable subframes are. It also explains why, as the previous slide, we have seen that also the system frame number, the radio frame where this configuration is applicable from onwards, is mentioned there, because we can't do that for all. And you see here an example bitmap with color-coded which particular subframe is addressed, and you see that we can create a semi-static scenario how these resources are shared. So semi-static instead of dynamic. So what does that mean? Well, like I said, in the cases that we have a single vendor scenario, we can call these dynamic spectrum sharing. That means with the proprietary internal scheduling algorithms influenced by parameters of how many LTE devices are there, how many 5G NR devices are there, what is the type of quality of service they are requesting, what is the overall load situation. These resources can be adjusted dynamically, and that's where the dynamic spectrum sharing is coming from. So last not least, a few words on testing. So the DS testing aspects on the devices for Insight, of course, you don't want to make sure you didn't break LTE. What you see here is ROHDE & SCHWARZ minimum footprint setup to test 5G NR and LTE. The very successful CMW 500 LTE test solution is extended with the CMX 500 providing the 5G NR, new radio capabilities. Of course, all these different features that I listed earlier need to be implemented and made available, which are, and the very initial step is we don't want to break LTE. That means we want to create an LTE cell that has an MBSFN subframe configuration and test, for instance, not only a 5G NR device, but also an LTE, a legacy LTE device to see that it can follow these instructions. That's the very initial step that we did and that we highlight in this particular video that you can watch at a later stage. The next step would be then, of course, to test the DSS functionality. ROHDE & SCHWARZ partnered with certain chipset vendors across the industry. Here, just one example with MediaTek and the validation of DSS using the CMX 500 platform. And again, I also put the video link into the description here, and you can find it on our YouTube channel in the web. So these are just a few aspects of it, how to test and look for DSS and verify it on chipset and devices, which brings us to a quick summary here. That DSS enables a rollout of 5G at FR1 frequencies without costly spectrum clearing and refarming. A different combination of feature sets enables DSS in the LTE 5G network. We took a look at the most important ones here. A device will submit specific capabilities that enable the support of DSS during the UE capability transfer during the initial registration process. And ROHDE & SCHWARZ is, of course, test solution for dynamic spectrum sharing, and I highlighted the portion on mobile radio communication testers. So thanks so much for watching, and keep your interest high on 35, a webcast series brought to you by ROHDE & SCHWARZ.